Hi class, it's Jamie Batts, your instructor for AMP2. We're continuing on with the lymphatic system. We just talked about the lymphatic organs, and now we're going to get into the innate response or the non-specific immunity. And let me switcheroni this. Whoops, that's not what I wanted to share. This is what I want to share. Sorry about that. I'm just going crazy. Is this my presentation? There we go. Sorry about that. So we are moving into innate immunity. This is the type of immunity that you're born with. So it doesn't matter whether you have been immunized or whether you were breastfed or whether you have vaccines or been exposed to pathogens before. This is the type of immunity that is our natural ability to defend itself, our body's natural ability. Hold on, I'm going to close my office door. This is usually I already have it closed, but my daughter's out there watching cartoons very, very loud. So anyways, all right, there are two mechanisms that work together to provide immunity. We have our innate immunity, which is the non-specific immunity. That's what we're focusing on right now. It does not distinguish from one type of invader or pathogen to another. It's, again, non-specific, right? The same response it's going to initiate the same response regardless of what the invader or pathogen or whatever it is. You're born with it, and it provides this non-specific resistance. So it's basically preventing things from attacking your body in general, right? So this is general stuff. Your adaptive immunity, this is what's going to utilize our adaptive defenses. So this is going to protect against particular threats, so a particular antigen, a particular virus, a particular bacteria, right? It depends on the activities of very specific lymphocytes, and it produces a state known as specific resistance. So our immunity can be broken down into innate defenses and adaptive defenses, or specific immunity and non-specific immunity. In our innate or specific non-specific immunity, we have several different mechanisms that are in place. We have our physical barriers, like our skin, phagocytes. These are the neutrophils and macrophages that are within our connective tissue and floating around in the blood, gobbling up, invaders. There's the immunological surveillance, like the natural killer cells that go around and detect those precancerous cells or virus-infected cells. Interferons, which are little cell hormones which destroy other virus-infected cells. Complement, which is something that we'll talk about in this chapter. Inflammation, as well as fever, all non-specific. So they're all going to respond the same way no matter what the invader or pathogen or immune driving issue is. You can pause the video here, go back and review this section. We're going to continue on and talk specifically about non-specific defenses, like our physical barrier. So this is mostly like our skin, right? The glands that are on the surface of our skin or on the surface of our integumentary system, they all have lysozymes in them. So the oil, the sweat, even the mammary secretions, milk, it all has lysozymes in it to help destroy any invaders. There's also antibodies included in our body secretions as well. And so our integumentary system is really our first line of defense. Hair included provides protection from mechanical abrasion. That's why we have hair on specific areas of our body, like around most of the body openings, our eyes, pubic regions, around our mouth, like especially in males, right? A lot around our eyes. And then the epithelial covering itself with that water-resistant keratin that's connected by desmosomes to allow it to twist and bend without being ripped apart very easily. So our integumentary system provides one of the first, actually the first line of defense. Other epithelial linings found along our digestive tract, the respiratory, urinary, reproductive tracts also function as our first physical barrier against invaders. Any secretions from these organs or from these tissues is meant to destroy or wash away any pathogenic material. MALT, that mucosa-associated lymphoid tissue, is another one. Phagocytes are another non-specific defense. They engulf and destroy any physical substance, or foreign substance rather, pathogens, any cellular debris. They're the first cellular line of defense. They are, sorry about this, just fixing my phone here. They attack and remove microorganisms even before the lymphocytes know that they're there. So again, one of the first lines of defense, phagocytes just going around gobbling things up. They're phagocytic, right? Different types are going to target different threats, but they all work in the same basic way through phagocytosis. The neutrophils, which are within the bloodstream and tissues, very fast-acting, phagocytize any debris, any bacteria. Eosinophils, much less abundant than our neutrophils are, but they phagocytize foreign compounds, any antibody-coated pathogens. Eosinophils are known for attacking any parasites in the body. So there's also a monocyte macrophage system, which is also known as the reticuloendothelial system. This is where macrophages, which are derived from monocytes, can basically become fixed or free. So if they're fixed, this is what I get for trying to do this during the day. Sorry about that. The fixed macrophages are basically immobilized within connective tissues. The free macrophages can float along in the body, and they can actually move into and out of being fixed or free. So they can lodge themselves in the connective tissue or dislodge themselves as they need to be. So, and again, the macrophages, you can just think of them as big old Pac-Man floating around trying to gobble up debris and bacteria. Here are some of the functional characteristics of phagocytes. They can actually leave the capillaries, as we've mentioned. This is called immigration or diapedesis. Right? This is just the migration or the movement of these cells into and out of different tissue areas. The phagocytes can be attracted by chemicals called chemotaxis. So they kind of smell, in a way, that there is damaged tissue or that there is a pathogen in the area, and they can respond accordingly. Phagocytosis typically begins when the cell itself, the macrophage, is attaching to the target, and then it will actually find certain receptors on that cell surface and then begin to engulf it. And then it can activate specific defenses after it has been engulfed. There's a phagocyte engulfing bacteria. The bacteria in this image are the orange rod-like structures, and the phagocytes are the big kind of yellow blobby things. You can pause the video here, go back and review this little section. Let's talk about immunological surveillance. So this constant monitoring of our normal tissues by natural killer cells is what's happening all the time. The normal cells are generally ignored, right? This is that recognition of self from non-self. Cancer cells contain tumor-specific antigens. So these natural killer cells can recognize the antigens on cancer cells, and it can bind to them and destroy them. They recognize bacteria as well as virus-infected cells as well. So the way they do this is through several steps. First, they will note that there is some type of unusual characteristic on the plasma membrane, and that's when the natural killer cell will adhere to that target cell. It'll say, you don't look like you belong here, right? One of these things is not like the other type of a thing. The Golgi apparatus within the natural killer cell is going to kind of creep towards the outer part of the natural killer cell, and within its secretory vesicles, it releases something called a perforin. A perforin is a chemical that's literally going to punch holes or perforate the other cell. So those perforins, which are released from the natural killer cell, go to the target cell and create pores or perforate that target cell. And then that target cell can no longer maintain its internal environment because it's leaking outside of itself, and therefore that target cell has been destroyed. That's how natural killer cells work. Here's a picture of it. It's floating along in step one, finds this abnormal cell, binds to it, recognizes it as an abnormal cell. The Golgi apparatus migrates, produces these perforins and secretory vesicles, which are released, perforate, and destroy that foreign cell, and then it's gone. Here are the steps individually, which I suggest printing out. Whenever there are these sequences in the PowerPoint, I suggest printing them out in sequence like that and seeing if you can summarize what's going on in the picture, because you literally just have like a picture right there that you can summarize and caption. There are mistakes that occur in cell division, and that is a natural process of living, and the natural killer cells will detect those mistakes that have been done in mitosis and natural cell division. So any abnormal daughter cells that occur during cell division, or any abnormal cells that become cancer cells, the natural killer cells will recognize and destroy in the same way, right, for those perforins. There's also something called immunological escape. So the immune surveillance that's done by these natural killer cells obviously isn't perfect, because we do get sick, right? We do have cells that become infected with viruses. We do have cells that are infected by bacteria. And unfortunately, some of our own cells become cancerous. So primary tumors can actually become surrounded in a capsule. And that's how they escape detection. So malignant cells will basically form this little capsule around themselves, and they'll kind of be like, hiding in secret. And when those malignant cells detach, they can then be detected and destroyed as they're trying to metastasize. Daughter tumor cells can actually not display any tumor-specific antigens as well. They will secrete chemicals that kill natural killer cells. So there's kind of this backlash against natural killer cells by tumor cells themselves. So cancer cells can then spread and form secondary tumors in some cases. Not all cancer cells respond like that. Some of them, we all have cancer popping up in our body right now, and thankfully our natural killer cells are doing their job. But sometimes there's some sneaky disguises that undergo. So the cells growing quickly within a primary tumor. The natural killer cells are trying to detect them, but they can't, because they are encapsulated, and then some of those daughter cells survive, and then they can spread and form secondary tumors. You can pause the video here, go back and review this section. Moving right along, let's talk about interferons, IFNs. Interferons are small proteins. They're actually released by lymphocytes. They're released by macrophages, and they're released by virus-infected cells. So they're little, like hormones almost, little like cell-to-cell signals. Sorry, my earring was bothering me. They're going to trigger the production of what we call antiviral proteins. So it's not going to prevent the entry of a virus, but it's going to interfere with viral replication. And that's what viruses do, right? They invade a cell, they take it over, and they make that cell make more copies of itself. So without the ability to replicate the virus, the virus is basically dead, right? So it can also stimulate the macrophages and natural killer cells. Cytokines are chemicals that are released by cells to coordinate these kind of localized activities that go on in response to the interferons. So there's three main types of interferons. There can be alpha interferons. These are produced by virus-infected cells to stimulate natural killer cells and enhance the kind of backlash against the viral infection. You have beta interferons, which are secreted by fibroblasts to kind of slow inflammation within a damaged area. And then there's gamma interferons, which are secreted by T cells and natural killer cells, and they're there to help stimulate macrophage activity. Here you see the three types of interferons, alpha, beta, and gamma, and their kind of target systems. The complement system is next. This is named because the system complements the action of antibodies. So there's over 30 special proteins that are within this complement system. And there's two pathways. So these proteins are basically interacting with one another in a chain or a cascade reaction, kind of like with blood clotting, where we had this intrinsic, it's my daughter, intrinsic and extrinsic pathway in blood clotting kind of coming together for the common pathway. You have the same idea here. Tori, can you please close the door to my office? Thank you, sweetie. So with complement, there are two possible pathways that occur, and it really just depends on kind of what's available. So the classical pathway and the alternative pathway. With the classical pathway, this is the most rapid and effective activation method. So this is where the complement proteins are going to attach to the antibody molecules. that are already bound to that pathogen, and it's going to activate and initiate this cascade of other complement proteins. So here you see the classical pathway. The antibodies are already bound, and the complement protein is going to cause this cascade. The alternative pathway is an important defense against bacteria and some virus-infected cells. Several complement proteins are going to interact within the blood plasma, which is basically triggered by a foreign antibody or foreign antigen exposure, and the end result is the activated complement protein becoming attached. So either way, you end up with this complement protein attached to the foreign body, right? So regardless of the pathway, regardless of whether we're going classical or alternative, the attachment of that complement protein is going to cause the pore formation and cellular lysis, so basically destroying that cell. Yeah, I was looking back at my notes to see if there was anything else to add, but there's really not. So the complement system has enhanced phagocytosis with it, so it's going to help attract phagocytes through a process called opsonization. I think of it as like optimization, like it's optimizing, kind of calling all the troops, so to speak, over to the target area to help engulf anything that needs to be gotten rid of. And there's also the histamine that's going to be released in response to this complement system. Histamine is released by mast cells and basophils to increase the inflammation, increase the blood flow to the area, sweep out the old and bring in the new type of a thing. So here you see this whole system, the alternative pathway or the classical pathway, either way, leading to an activated complement protein on the surface of our invader, and that's going to lead to pore formation and cell lysis or phagocytosis or histamine release. So there's the whole system kind of graphed out for you, and it really just has to, the difference between the alternative and classical pathway really just have to do with how it is activated. The alternative pathway is activated by plasma factors. The classical pathway is really just activated by the specific antigen and the chain reaction. So you can pause the video here, go back and review these 3 questions. We're going to continue on with this section and talk about inflammation. The inflammatory response is a localized response that causes redness, swelling, heat, pain, and sometimes loss of function in that particular area. It can be caused by a variety of stimulus that kills cells. It could damage connective tissue. It could be caused by injured tissue. So basically, it's going to cause a change in the chemical composition of that interstitial fluid and those damaged cells, releasing prostaglandins, proteins, and potassium ions. Foreign proteins and pathogens that have been introduced all can bring on inflammation. This is going to trigger a complex inflammatory response. So we have tissue damage. This is because those cells have been ruptured. Those cells are going to release chemicals. The chemicals trigger mast cells to be activated. Mast cells will then release histamine and heparin, and the histamine and heparin are going to bring about this inflammatory response. You're going to get the redness, the heat, the swelling, the pain, as well as the attraction of phagocytes because of the release of cytokines, basically those cell messengers saying, hey, we need some help over here, we have some damage, etc. Eventually the tissue is repaired, the scars formed, etc. With fever, you have a body temperature greater than 99 degrees. This is brought on by pyrogens. Pyrogens are basically fever-inducing proteins. They can help reset the thermostat in the hypothalamus. So basically, they turn off that part of the hypothalamus that says, uh-oh, our body temperature is getting up, we need to start sweating, right? That doesn't happen. And so it allows your body temperature to rise. This can be beneficial within limits, right? Fevers are built-in natural defense mechanism for infections and invaders. So it can inhibit the growth of some viruses and bacteria. It helps by increasing our metabolic rate to increase the tissue defenses and the overall repair process throughout the body. So overall innate immunity. And here's what I want you to do with this. I have a graphic organizer, but I'm not going to draw it for you. I want you to do it. In the center, you have innate immunity or non-specific defenses. It's all the same, right? Off of it, you're going to have a branch for physical barriers. Off of your branch for physical barriers, you're going to have a couple different types of physical barriers, like the epithelial linings, your skin, your hair, your glands, right? All of that. Then you have phagocytes. Then you have immunological surveillance, interferons, right? All of these things that we just talked about, fever, inflammation, all coming off of this graphic organizer. Draw it out, add information, add drawings, specifics, right? Details. When you graph it out, you're going to remember it more. The more colorful and animated you are when you create this graphic organizer, the more likely you are to remember it when you're studying. So here are some of our physical barriers, phagocytes, and immunological surveillance. And then, of course, our complement system, inflammation, and fever. And you can stop the video here, because I'm going to stop the video here. This is the end of this section of Chapter 20. So let me know what questions you have. Have a super awesome day.